In the summer of 2022, when the world had barely begun to shake off the weight of a pandemic that had rewritten the rules of human gathering and reminded everyone of their fragility, a machine built over more than 2 decades by thousands of hands finally opened its golden eye in the darkness beyond the moon, and what it saw would rewrite humanity's understanding of the universe in ways that no one, not even the scientists who had spent their entire careers building it, could have fully anticipated. The James Webb Space Telescope hung suspended at a mathematical fiction called Lagrange Point 2, a place where the gravitational pulls of Earth and Sun balanced so perfectly that an object could remain there with minimal fuel expenditure, a cosmic perch nearly 1 million miles from the world that birthed it, 4 times farther than the moon that had once represented the outer limit of human ambition. This was not a telescope in the way most people understood the word, not a simple tube with lenses that magnified distant objects, but rather a time machine of sorts, designed to capture light that had been travelling through the void for more than 13 billion years, light that left its source when the universe itself was still in its infancy, a cosmic nursery of the first stars and galaxies. The story of how humanity came to place such an instrument in the heavens began not with a single decision or a dramatic moment of inspiration, but with a slow accumulation of frustration and ambition that had been building in the astronomical community since the 1980s, when the Hubble Space Telescope was still being assembled and its eventual problems were yet to be discovered. Even before Hubble launched in April of 1990, astronomers were already thinking about what would come next, because they understood something fundamental about the nature of scientific instruments. Each answer generates 10 new questions, and each new window into the cosmos reveals how limited the previous window had been. The Hubble, for all its eventual glory after its corrective surgery in space, was fundamentally limited by the size of its mirror, just 2.4 meters across, and by its design, which focused primarily on visible and ultraviolet light, the same portions of the electromagnetic spectrum that human eyes could detect, leaving vast swaths of infrared radiation unexplored, radiation that held secrets about the universe's earliest moments and the birth of stars hidden behind cosmic dust. In 1996, when Hubble had been operating successfully for several years following its repair and was sending back images that transformed public understanding of space, a group of astronomers and engineers gathered at the Space Telescope Science Institute in Baltimore, Maryland, in rooms that still smelled of new carpet and coffee that had been sitting too long on the burner, to begin seriously planning what they initially called the Next Generation Space Telescope. The meeting rooms had windows that looked out over the Johns Hopkins University campus, where leaves were turning autumn colours, and inside those rooms, people drew sketches on whiteboards and passed around preliminary designs that looked nothing like what would eventually fly, because at that stage nobody really knew if what they wanted to build was even possible. They knew they wanted a mirror much larger than Hubble's, perhaps 8 meters across, and they knew they wanted to focus on infrared light, which required keeping the telescope incredibly cold, colder than any spacecraft of such complexity had ever been maintained, because infrared is essentially heat radiation, and a warm telescope trying to detect infrared would be like trying to study fireflies while holding a torch. The challenge was not merely technical but political and financial, because the National Aeronautics and Space Administration had been burned before by cost overruns and schedule delays, and Congress had long memories when it came to space projects that promised one thing and delivered another, years late and billions over budget. The Hubble itself had been a cautionary tale in this regard, with its initial flawed mirror that had resulted from a measuring error so small it seemed impossible, yet which had nearly destroyed the program's credibility until astronauts risked their lives to install corrective optics in one of the most delicate operations ever performed in orbit. So when the astronomers began pitching their next-generation space telescope, they did so with carefully constructed budgets that projected a total cost of around $500 million and a launch date sometime in the early 2000s, projections that would prove to be wildly, almost comically optimistic, Though nobody laughed when the real numbers finally came in, the fundamental problem was that to see the earliest galaxies and the first stars, the telescope needed to be optimized for infrared wavelengths, particularly the mid and far infrared, where the light from those ancient objects had been stretched by the expansion of the universe itself, a phenomenon called redshift that transformed what had once been visible and ultraviolet light into infrared by the time it reached Earth's neighborhood. This meant the telescope's instruments had to be kept at temperatures approaching absolute zero, around 40 degrees Kelvin or colder, which is negative 233 degrees Celsius, cold enough that nitrogen freezes solid and carbon dioxide becomes a distant memory. Achieving this in space required not just insulation, but active cooling systems, and, more importantly, keeping the telescope permanently shaded from the sun's heat, which meant it could not orbit Earth like Hubble did, because Earth itself would alternately heat and block the instrument as it circled. The solution was Lagrange point 2, that gravitational sweet spot where Earth and Sun aligned in such a way that a massive sun shield could protect the telescope from both bodies simultaneously. The sun shield became one of the defining challenges of the entire project, a structure the size of a tennis court, composed of 5 layers of material so thin it was measured in thousandths of an inch, each layer separated from the next by a gap that allowed heat to radiate away into space, creating a temperature difference of more than 500 degrees Fahrenheit between the sun-facing side and the shaded side where the telescope itself would sit. The material chosen was a form of Kapton, a polyamide film developed in the 1960s by DuPont, coated with aluminum and, on the outermost layers, a silicon compound that reflected the sun's heat like a cosmic mirror. Manufacturing these sheets to the required precision meant developing entirely new production techniques, because any flaw, any microscopic tear or weak point could propagate in the vacuum of space and potentially destroy the mission. The engineers who worked on this problem spent years testing materials in vacuum chambers, subjecting them to thermal cycles that simulated the extreme conditions of space, and learning the hard way that some solutions that worked on Earth failed catastrophically when the air was removed and temperatures swung wildly. By the year 2000, the project had acquired a name that would stick: the James Webb Space Telescope, named after NASA's second administrator, who had led the agency during the Apollo build-up in the 1960s, a choice that seemed straightforward at the time but would later generate controversy when historians re-examined Webb's record on civil rights and his possible role in purging gay employees from the State Department in the 1950s. But in 2000, with the new millennium dawning and technology stocks soaring before their inevitable crash, the naming seemed like a way to honour NASA's history while looking toward its future, and few people questioned whether Webb was the right figure to represent this scientific endeavour. The budget estimates had already grown to around $1 billion, double the original projection, and the launch date had slipped to 2010, which seemed far enough away that surely all the technical challenges could be resolved. The mirror design represented a revolution in space engineering, because unlike Hubble's single piece of precisely ground glass, Webb's primary mirror would be composed of 18 separate hexagonal segments, each 1.3 meters across, made of beryllium, a metal chosen for its unique combination of stiffness, lightweight, and stability at cryogenic temperatures. Beryllium is also toxic when machined, requiring workers to operate in full protective gear as they ground each mirror segment to a precision measured in nanometers, then coated each one with a microscopically thin layer of gold, about 100 nanometers thick, roughly 1,000 atoms deep, because gold reflects infrared light better than aluminum and would give the telescope the sensitivity it needed. Each mirror segment would be controlled by 7 tiny motors called actuators that could adjust its position with incredible precision, allowing the 18 pieces to function as a single 6.5 meter mirror, adjustable even in the coldness of space, compensating for the minute shifts and vibrations that would inevitably occur. The engineers faced a problem that seemed insurmountable in the early 2000s. The The telescope was too large to fit inside any existing rocket fairing, the protective nose cone that shields satellites during launch. Unlike Hubble, which was built to fit snugly in the Space Shuttle's cargo bay, Webb would have to fold up like cosmic origami, with the mirror segments hinged to fold back on themselves. The sunshield compressed into a space barely larger than a car, and the entire assembly designed to unfold automatically in space through a sequence of deployments so complex that it involved over 300 single points of failure, any one of which could doom the mission. There would be no repair mission, no astronauts arriving in a spacecraft to fix problems as they had with Hubble, because Webb would be operating nearly 1 million miles from Earth, well beyond the reach of any human crew with current technology. It had to work perfectly the first time, unfolding itself through a series of precisely choreographed movements, executed by motors and release mechanisms that had to function flawlessly after being subjected to the violent shaking of launch and the temperature extremes of space. Testing this deployment sequence became an obsession for the engineering teams, who built full-scale models and subjected them to every imaginable condition. But testing in Earth's gravity proved nearly impossible, because the structures that would float effortlessly in space sagged and bent under their own weight on the ground. The teams had to develop special support structures and conduct many tests underwater, where neutral buoyancy could simulate some aspects of weightlessness. The water introduced its own complications and could never fully replicate the vacuum of space. The sunshield particularly vexed them, because folding 5 tennis court-sized layers of thin film so they would unfold correctly in space, without tearing or tangling, seemed to violate basic principles of probability. Each layer had to be precisely tensioned after deployment, pulled tight by cable systems that had to work in perfect coordination. And during ground tests, these systems failed repeatedly, the thin material catching on itself, tearing at attachment points, behaving in ways the computer models had not predicted. Meanwhile, the scientific instruments being designed to ride aboard the telescope represented their own frontiers of technology. The near-infrared camera, called NIRCam, would serve as both a primary imager and the wavefront sensor used to align the mirror segments, employing detectors so sensitive they could register individual photons arriving after journeys of billions of years. The near-infrared spectrograph, NIRSpec, featured a micro-shutter array containing 250,000 tiny shutters, each smaller than a human hair is wide, that could be individually opened or closed to allow light from specific galaxies to pass through for spectral analysis, while blocking light from unwanted sources, a technology that required developing tiny magnetic actuators that could operate reliably at 40 degrees Kelvin. The mid-infrared instrument, MIRI, needed to operate even colder than the rest of the telescope, below 7 degrees Kelvin, requiring its own dedicated cooling system, a cryocooler that used helium gas in a closed loop to reach temperatures where even the molecules in air would freeze solid, if there were any air. By 2005, the projected cost had ballooned to $3 billion, and the launch date had slipped to 2014, causing considerable alarm in Congress, where appropriators were already dealing with cost overruns on numerous other NASA programs. The Space Shuttle Columbia had disintegrated during re-entry in 2003, killing 7 astronauts and casting a shadow over NASA's competence, and administrators knew they could not afford another high-profile failure. Independent review boards were convened, producing reports with titles that contained words like management challenges and risk assessment, polite Washington language for serious problems. The reviews found that the project's complexity had been systematically underestimated, that the technologies required were in many cases being invented as the telescope was being built, and that the management structure spread across multiple NASA centers and international partners created coordination challenges that delayed decision-making and obscured responsibility. The international dimension added both capability and complexity, because Webb was not solely an American project, but a collaboration involving the European Space Agency and the Canadian Space Agency, each contributing specific instruments and expertise. ESA provided NIRSPEC and a share of MIRI, along with the Ariane 5 rocket that would ultimately launch the telescope, a contribution valued at hundreds of millions of euros and representing Europe's continued commitment to space science, despite economic pressures and political skepticism about expensive scientific projects. Canada contributed the Fine Guidance Sensor, a near-infrared imager, and slitless spectrograph, precision instruments that would allow the telescope to lock onto targets with extraordinary accuracy and study them across multiple wavelengths. This international cooperation meant coordinating schedules and technical specifications across continents, time zones, and organizational cultures, with engineers in Maryland needing to interface with colleagues in Toulouse and Toronto, sharing designs through secure systems, and resolving disagreements through video conferences that often occurred at inconvenient hours for at least one party. The primary contractor was Northrop Grumman, an aerospace giant known for building stealth bombers and surveillance aircraft, perhaps an odd choice for a scientific instrument, but one that made sense given the company's expertise in precision structures and complex deployable systems. In a massive clean room in Redondo Beach, California, workers dressed in full-body suits that made them look like characters from a science fiction film assembled the telescope piece by piece, each component cleaned to standards that would seem obsessive in any other context but were merely prudent here, because even a single particle of dust on a mirror or instrument could scatter light and degrade performance. The cleanroom itself was a testament to extreme engineering, with air filtered to remove particles larger than half a micron, pressure kept slightly above the outside atmosphere so that air flowed outward when doors opened, preventing contamination from entering, and humidity controlled to prevent moisture from condensing on the ultra-cold components during testing. By 2010, the year Webb had originally been scheduled to launch, the telescope existed only as partially assembled components in various facilities, and the budget had grown to over $5 billion with a new launch target of 2015. Members of Congress began questioning whether the project should be cancelled, whether throwing good money after bad made any sense when NASA had other priorities and the nation was struggling through the aftermath of the 2008 financial crisis. In 2011, the House Appropriations Committee actually voted to terminate funding for Webb entirely, a decision that sent shockwaves through the astronomical community and prompted an unprecedented lobbying effort by scientists who argue that cancelling the telescope now, after billions had been spent and the technology proven feasible, would waste all that investment and cede leadership in space astronomy to other nations. The Senate restored the funding, but with stringent caps on future spending and requirements for regular progress reviews, and NASA administrators knew they were operating under what was effectively probation. The crisis forced a reorganization of the project management and a more realistic assessment of what remained to be done. Engineers developed new schedules that built in contingency time for problems, something the earlier optimistic timelines had lacked, and they implemented more rigorous testing protocols that caught problems on the ground, rather than discovering them later when fixes would be far more expensive. The Sunshield deployment mechanism was completely redesigned after tests showed the original system was unreliable, with new release mechanisms and tensioning systems that added weight and complexity, but dramatically improved the probability of success. Each mirror segment was tested individually in a cryogenic chamber that could simulate the temperature and vacuum of space. Then the segments were tested together as a complete array, a process that revealed subtle interactions and alignment challenges that computers had missed. In 2016, the 18 primary mirror segments were finally brought together and assembled into the complete primary mirror array at NASA's Goddard Space Flight Center in Maryland, where engineers worked in another massive clean room, this one with viewing galleries where visitors could watch through thick glass windows as the golden hexagons were slowly, carefully mated to the backplane structure that would hold them in space. Each segment weighed about 40 pounds on Earth, though of course it would weigh nothing in space, and each one represented years of work by teams of specialists who had learned to work with beryllium's peculiar properties who had developed the polishing techniques to achieve the required shape accuracy, and who had applied the gold coating with such precision that it varied in thickness by no more than a few nanometers across the entire surface. When all 18 segments finally sat together, the assembled mirror looked like a giant golden flower, alien and beautiful, reflecting the clean room lights in ways that seemed to shift and shimmer as viewers moved their heads. Testing the complete mirror assembly required a device called the Optical Ground Support Equipment, essentially a sophisticated artificial star that could project known patterns of light into the telescope, while instruments measured how accurately the mirror focused that light, allowing engineers to adjust each segment's position until all 18 pieces worked as one. This testing happened inside a chamber called the Space Environment Simulator at Johnson Space Center in Houston, a facility originally built to test Apollo hardware, now repurposed to hold the Webb telescope in conditions that approximated the vacuum and cold of space, though truly replicating the deep cold required for full operations was impossible on Earth. The chamber was large enough to hold the entire telescope, with walls painted black to absorb stray light and liquid nitrogen running through pipes in the walls to cool the interior to around 50 degrees Kelvin, cold enough to make most materials brittle, and to create thermal stresses that had to be carefully managed to avoid damaging the delicate instruments. The integration of the scientific instruments took years longer than planned, not because of any single catastrophic problem, but because of the accumulated complexity of mating instruments built by different teams to a telescope structure that was itself still evolving as engineers discovered and fixed issues. Each instrument had its own personality, its own quirks and requirements, and getting them all to work together required endless meetings and negotiations between teams who sometimes had competing priorities and different institutional cultures. The Europeans working on NR-Spec had different testing protocols than the Americans working on NR-CAM, and reconciling these differences while ensuring that nothing was overlooked required patience and diplomacy alongside technical skill. When problems were discovered, as they inevitably were, deciding who would pay for the fixes and how they would be implemented required navigating the complexities of international agreements and organizational budgets. In 2017, during vibration testing that simulated the violent shaking of launch, several screws and washers came loose from the sunshield structure, rattling around inside the folded assembly in a way that could have caused catastrophic damage during deployment. The incident forced a months-long investigation to determine how the fasteners had failed, redesign the attachment methods, and retest everything to ensure the problem would not recur. This kind of discovery, terrifying but ultimately fortunate because it happened on the ground where it could be fixed, illustrated why the testing was so extensive and why the schedule kept slipping. Better to find problems in a clean room in California than to discover them a million miles away in space where nothing could be done. By 2018, the projected launch date had moved to 2021, and the total development cost had reached nearly $10 billion, making Webb one of the most expensive scientific instruments ever built, exceeding the inflation-adjusted cost of Hubble and rivaling some major particle physics facilities. Critics questioned whether any single instrument could be worth such expenditure, whether the money might have been better spent on multiple smaller missions that could distribute the risk and potentially produce results sooner. Defenders pointed out that Webb's capabilities were unique, that it would be able to observe phenomena that no other existing or planned telescope could study, and that the technologies developed for Webb were already finding applications in other fields, from medical imaging to semiconductor manufacturing, though these spin-off benefits were difficult to quantify and even harder to use as justification for the enormous cost. The telescope finally came together in its flight configuration at Northrop Grumman's facility in 2019, with the mirror array mated to the instrument module and the entire assembly attached to the spacecraft bus that would provide power, communications, and propulsion. The complete observatory, as the integrated system was called, looked bizarre, utterly unlike any spacecraft that had flown before, with its golden mirrors and enormous folded sunshield, creating an asymmetric shape that seemed more like sculpture than engineering. Testing this complete assembly required yet another round of environmental simulations, acoustic tests, where speakers blasted sound at levels that would rupture eardrums to simulate the noise of launch, an electromagnetic compatibility test to ensure that the various systems would not interfere with each other's delicate electronics. Then came 2020 and the global pandemic that shut down facilities around the world, forcing engineers to work from home on projects that had always required hands-on presence, video conferencing about problems that were much easier to solve when everyone could gather around the actual hardware. The launch date slipped again to October 2021, then November, then December, and with each delay the costs mounted, not just from continued salaries and facility operations, but from the opportunity cost of scientists waiting to use an instrument that remained frustratingly out of reach. The astronomical community had planned their careers around Webb's capabilities, writing proposals for observations years in advance, and some scientists who had been young researchers when the project began were now approaching retirement, wondering if they would get to see the data they had spent decades anticipating. The telescope was shipped to French Guiana in the autumn of 2021, transported in a special container aboard a vessel that took weeks to make the journey from California through the Panama Canal to the port of Pariacabo, then by truck to the launch site at Kourou, where the European Space Agency operated its spaceport just 5 degrees north of the equator. The location offered advantages for launching heavy payloads because the Earth's rotation provides extra velocity at the equator, effectively giving rockets a free boost, and because the trajectory over the Atlantic Ocean meant falling debris would land in water rather than populated areas. The launch facility sat in a landscape of tropical forest and beach, where macaws flew past gantries and iguanas basked near blockhouses, an incongruous setting for such advanced technology. At Kourou, teams began the final preparations, carefully removing the telescope from its shipping container in another clean room, inspecting every surface and system to ensure nothing had been damaged during transport, then slowly, methodically, fueling the spacecraft with hydrazine propellant that would power the thrusters used for course corrections and maintaining position at Lagrange Point 2. Hydrazine is viciously toxic, requiring handlers to wear full protective suits with their own air supplies, and loading it into the spacecraft's tanks required such care that the process took days. Then came mating the observatory to its Ariane 5 rocket, a process that involved lifting the multi-ton telescope assembly with overhead cranes and slowly over the course of hours, lowering it onto the rocket's upper stage while engineers monitored clearances measured in millimeters, ensuring that nothing bumped or scraped. The Ariane 5 that would launch Webb had its own impressive pedigree, a rocket that had been launching satellites successfully for over 2 decades, with a reliability record that made it one of the most trusted launch vehicles in the world, though even with dozens of successful flights, each launch still carried risk, still depended on millions of components functioning exactly as designed during the violent, roaring ascent to orbit. The rocket stood over 50 meters tall, painted white with orange insulation foam on its core stage, and 2 massive solid rocket boosters strapped to its sides, each booster containing over 200 tons of solid propellant that would burn for just over 2 minutes, producing thrust that would be felt as violent shaking inside the payload fairing where the telescope sat. Launch was scheduled for December 24th, 2021, Christmas Eve, a timing chosen not for symbolism but because it fell within the window when all systems were ready and weather conditions were acceptable. In the days before launch, teams worked around the clock running final checks, testing communications links, verifying that every one of the thousands of pyrotechnic devices that would fire during deployment were properly connected and armed, that batteries were charged, that solar arrays were ready to deploy once the telescope separated from the rocket. The night before launch, senior engineers and scientists gathered for a final review, going through checklists that ran to hundreds of pages, each item requiring a verbal confirmation that it had been completed satisfactorily. A ritual that took hours and left everyone exhausted but confident that everything humanly possible had been done to ensure success. On the morning of December 24th, under skies that threatened rain but remained just clear enough, the Ariane 5 lifted off from its pad with a roar that echoed across the jungle, its solid boosters producing brilliant orange flames and white smoke that billowed around the launch pad. Inside the payload fairing, the James Webb Space Telescope experienced accelerations and vibrations that would have destroyed it, if not for the careful engineering of its structure and the shock absorbers that isolated it from the worst of the violence. The flight to orbit lasted about 27 minutes, with the solid boosters burning out and separating, the first stage expending its liquid hydrogen and oxygen and falling away, the upper stage igniting and pushing the telescope higher and faster, until finally, on the far side of the world from where it started, the fairing split in half and fell away, exposing the telescope to the vacuum of space for the first time. Separation from the rocket occurred precisely on schedule, and within minutes the telescope deployed its solar array, a 5-layered structure about the size of a conference table that would provide the electricity to power the spacecraft's systems, and controllers in Baltimore received the first telemetry confirming that the spacecraft was alive, oriented correctly, and communicating properly with the ground. The relief in the control room was palpable but tempered by the knowledge that this was just the beginning, that the most challenging part of the mission was still to come during the 6 months of deployments and commissioning that would transform the folded dormant machine into a functioning observatory. The journey to Lagrange Point 2 would take a month, following a carefully calculated trajectory that was deliberately designed to ensure that if anything went wrong during deployment, the telescope could not accidentally fall back toward Earth and burn up in the atmosphere, destroying the evidence that investigators would need to understand the failure. This trajectory required 3 course correction burns, adjustments to the velocity and direction using the spacecraft's thrusters, each burn calculated to within millimeters per second of accuracy, to ensure arrival at precisely the right point in space, with precisely the right velocity. The first burn occurred 12 hours after launch, a relatively large maneuver that consumed several kilograms of propellant and set the telescope on its path away from Earth. Each kilogram precious, because once the hydrazine was gone, the mission would end, unable to maintain its position or orient itself. 3 days after launch, the Sunshield began its deployment sequence, starting with the lowering of pallets that had held the folded layers against the spacecraft during launch. This operation used motors that had been tested thousands of times on the ground, but had never operated in the actual environment of space, and everyone watched the telemetry with anxiety, looking for any sign that something was catching or binding. Each step took hours rather than minutes, executed with deliberate slowness to allow controllers to assess the situation and halt the process if any anomaly appeared. And because many of the mechanisms were one-shot devices, pyrotechnic release mechanisms that use small explosive charges to sever cables or release catches, irreversible actions that had to be commanded with absolute certainty they would work as intended. The Sunshield layers separated and began to unfold, each one slightly larger than the one above it, creating a precisely calculated gap between layers that would allow heat to radiate away while preventing direct thermal contact. The tensioning system activated, with cables pulling each layer tight through a complex system of pulleys and release mechanisms, transforming wrinkled film into taut surfaces that resembled enormous kites floating in space. During this process, one of the tensioning motors showed higher than expected current draw, suggesting it was working harder than it should, possibly because of friction or a slight misalignment, and for several tense hours, engineers analysed the data, running simulations to determine whether to proceed or stop and try to diagnose the problem. They concluded that the motor was still within acceptable limits, that the higher current likely resulted from normal variation in the deployment rather than a failure, and the tensioning continued, ultimately completing successfully with all 5 layers deployed and taut. 2 weeks after launch, with the sunshield deployed and beginning to create the thermal environment the telescope needed, controllers commanded the deployment of the secondary mirror, a smaller convex mirror mounted on 3 struts that would intercept light from the primary mirror and reflect it back through a hole in the primary to the instruments behind. This deployment involved releasing latches and allowing the tripod structure to swing forward and lock into position, another irreversible operation that had to work perfectly, because the secondary mirror was essential to the telescope's optical design, and without it properly positioned, the entire instrument would be useless. The mechanism worked flawlessly, the latches releasing and the tripod swinging into position with a positive lock conformation that produced cheers in the control room. The primary mirror deployment came next, with the 2 wing sections that held 6 mirror segments, each swinging outward from their folded position alongside the central section, rotating on hinges that had to work despite temperature extremes and months of inactivity since testing. The starboard wing deployed first, a process that took about 5 hours as motors slowly rotated the wing from its stowed position 90 degrees out to its operating position, where additional latches engaged to lock it firmly in place. The port wing followed 2 days later, completing the full primary mirror array, and for the first time since leaving Earth, the telescope looked approximately as it would when operating, with its full 6.5 meter mirror exposed to space, though still far too warm to begin observing. Cooling the telescope to its operating temperature would take months, a passive process that could not be rushed, as heat slowly radiated away into the cold of space from the shaded side of the sunshield. Instruments and mirror segments gave up their warmth through radiation, losing a few degrees each day, following cooling curves that engineers had predicted with computer models, but which still had to be verified with actual temperature sensors embedded throughout the structure. As the temperature dropped, materials contracted, and the shape of the mirror segments changed slightly, predictable changes that would later be corrected by adjusting the actuators behind each segment, but which had to be monitored carefully to ensure nothing contracted so much or so unevenly that it caused structural problems. While the telescope cooled, engineers began the process of aligning the mirror segments, a task of extraordinary precision that would take 3 months to complete fully. Each segment had to be positioned and tilted so that light reflecting from it would combine coherently with light from all the other segments, creating a single unified wavefront as if the 18 pieces were one perfect mirror. The process began by using NIRCam to take images of a bright star, images that initially showed 18 separate points of light because the segments were still pointed in slightly different directions, creating 18 separate images of the same star. Over weeks, engineers adjusted the actuators behind each segment, watching as the 18 points of light slowly moved closer together, converged, and finally merged into a single bright point, surrounded by the diffraction pattern that indicated proper focus. Fine-tuning this alignment required iterations beyond counting, tiny adjustments to each segment's position and tilt, checking the results, adjusting again, a process called wavefront sensing and control that pushed the limits of optical engineering. The goal was to align the segments so precisely that the entire mirror would produce images limited only by the physics of diffraction, the fundamental limit imposed by the wave nature of light itself, rather than by imperfections in the mirror's shape or alignment. Achieving this required measuring and correcting errors smaller than the wavelength of light, adjustments measured in nanometers, movements so small that they seemed impossible to control, yet the actuators proved capable of making these adjustments and holding them stable even as the telescope's temperature continued to drop and the structure continued to shift microscopically. By March of 2022, the alignment had progressed to the point where the telescope could take test images that revealed its true capabilities, and when astronomers released one of these images to the public, a deep field showing thousands of galaxies in a tiny patch of sky? The response was immediate and overwhelming. People who had never heard of the James Webb Space Telescope suddenly saw images that looked like nothing Hubble had produced, with details and colours that seemed almost artificial in their clarity. Galaxies stretched and distorted by gravitational lensing from massive galaxy clusters in the foreground. Their light shifted so far into the infrared that without Webb's specialised instruments they would have been invisible. The image showed not just nearby galaxies but objects from the early universe, their light travelling for more than 13 billion years to reach the telescope's mirrors, photons that had been emitted when the universe was only a few 100 million years old, when the first galaxies were still forming from primordial clouds of hydrogen and helium. The first science images were released in July 2022 at a coordinated event that involved NASA, ESA, and scientific institutions around the world, with the initial image unveiled by the President of the United States in a White House ceremony that seemed designed to emphasize the telescope as a national achievement. Though the science community somewhat awkwardly navigated the political dimensions, wanting to celebrate the accomplishment while recognizing the international contributions and the fact that science transcends national boundaries. The images released that day showed a range of targets chosen to demonstrate Webb's versatility. The Carina Nebula with its towering pillars of gas and newborn stars bursting through, the Southern Ring Nebula with its dying star shedding shells of gas in concentric rings, Stephan's Quintet, a group of 5 galaxies locked in a gravitational dance, and spectral analysis of an exoplanet's atmosphere revealing the signatures of water vapour. Each image revealed details never seen before, structures in nebulae that suggested new questions about how stars form, galaxies whose morphologies challenged existing theories about galaxy evolution, exoplanet atmospheres whose chemical compositions could be analysed with precision that had been impossible just months earlier. The Carina Nebula image showed cliffs of gas that looked almost geological, with bright young stars at the peaks, their radiation and stellar winds eroding the gas around them and revealing dense knots that were perhaps future stars still forming. The resolution was such that individual structures could be picked out, knots and filaments that were smaller than the distance between stars, details that would allow astronomers to test their theories about turbulence and magnetic fields and the complex physics of star-forming regions. The spectrum of the exoplanet WASP-96 showed absorption lines indicating water vapour in the planet's atmosphere, a finding that was scientifically significant but also carried cultural weight because water suggested connections to Earth, to the possibility of life elsewhere, even though this particular planet was a hot gas giant orbiting far too close to its star to host anything resembling terrestrial life. The spectrum represented a new era in exoplanet science, where instead of merely detecting planets by their gravitational effects on their stars or by the dimming as they passed in front of their stars, astronomers could now analyse the chemical composition of their atmospheres by measuring how starlight filtered through those atmospheres during transits, revealing the presence of specific molecules based on which wavelengths were absorbed. Webb's infrared sensitivity meant it could detect molecules like carbon dioxide and methane that were difficult or impossible to see with visible light telescopes, opening the possibility of finding biosignature gases that might indicate biological processes on distant worlds. The deep field image showed galaxies so distant that their light had been travelling since the universe was less than 5% of its current age. Galaxies that appeared as they were shortly after the first stars formed, when the universe was emerging from the cosmic dark ages, the period after the cosmic microwave background radiation was emitted, but before stars and galaxies rionized the hydrogen that filled intergalactic space. Some of these galaxies appeared unexpectedly large and bright for their age, challenging models that predicted how quickly galaxies could grow in the early universe, suggesting that perhaps the process of galaxy formation was more efficient than theorists had assumed, or that the first stars were different from modern stars in ways that affected how galaxies evolved. These discrepancies between observations and theory were exactly what astronomers had hoped for, because confirming what was already believed would be far less interesting than discovering phenomena that required new explanations. As Webb entered its operational phase, with science observations beginning in earnest, the telescope started working through a schedule of observations that had been planned years in advance, a queue of targets proposed by astronomers from around the world and selected through a competitive peer review process. Some observations were short, just a few hours to capture a spectrum or image a specific target, while others required hundreds of hours spread over months, building up extremely deep exposures that could detect the faintest objects possible. The scheduling was complex, constrained by the telescope's need to avoid pointing anywhere near the Sun or Earth, which sat together in the same direction from Webb's perspective, limiting observations to a band of sky that rotated over the course of the year as the telescope orbited the Sun along with Earth, maintaining its position at Lagrange point 2. Observations of the most distant galaxies revealed that the early universe contained a surprising diversity of galaxy types and sizes, with some galaxies appearing to be massive spirals that conventional theories suggested should not have had time to form yet, while others were compact and irregular, perhaps caught in the act of merging or still assembling from smaller fragments. The data challenged astronomers to reconsider their timelines for cosmic evolution, to question whether the standard cosmological model needed adjustment, or whether the observations were being misinterpreted, whether what appeared to be very distant galaxies might actually be something else, though the spectroscopic data confirming their distances seemed solid. The debates that erupted in scientific journals and conferences were vigorous, with different teams analysing the same data and reaching different conclusions, exactly the kind of scientific controversy that drives progress by forcing everyone to examine their assumptions and refine their methods. Studies of star-forming regions closer to home within our own galaxy showed that the process of star formation was even more complex than previously understood, with feedback from newly formed stars affecting the surrounding gas in intricate ways, triggering some regions to collapse and form more stars while disrupting other regions and preventing further collapse. Images showed structures that looked like fingers and pillars, dense columns of gas pointing toward the brightest young stars, their shapes sculpted by radiation pressure and stellar winds, and within these pillars, embedded protostars appeared as bright infrared sources, their visible light still trapped by surrounding dust, but their heat radiation pouring out in wavelengths that Webb could detect. Spectroscopy of these regions revealed the chemical composition of the gas, showing not just simple hydrogen and helium but complex molecules, organic compounds that formed in the cold darkness of molecular clouds, and which would later be incorporated into planets and potentially into life. Observations of nearby galaxies allowed astronomers to study star formation and galactic structure with unprecedented clarity, resolving individual star-forming regions in galaxies millions of light-years away, mapping the distribution of dust and gas, and tracing the complex architecture of spiral arms and galactic bars. Some of these observations revealed that many galaxies contained massive black holes at their centres that were actively feeding on surrounding matter, producing enormous amounts of energy as material spiraled inward and heated to millions of degrees before crossing the event horizon. The infrared light Webb detected could penetrate the dust that often obscured these active galactic nuclei in visible light, revealing the structure of the accretion disks and the jets of material being blasted outward at relativistic speeds. The telescope's study of exoplanet atmospheres expanded rapidly as astronomers pointed it at dozens of different systems, building up a catalogue of atmospheric compositions that began to reveal patterns and categories. Some hot Jupiters showed evidence of clouds made of silicate particles or exotic compounds that would never form in Earth's atmosphere, while others appeared relatively clear, allowing deeper observations into their atmospheric layers. Smaller planets, closer in size to Earth though mostly still too hot to host liquid water, showed different chemical signatures, with some displaying abundant carbon dioxide or methane, while others seemed to have atmospheres rich in hydrogen and helium that they had retained from the protoplanetary disk or atmospheres that had been extensively processed by stellar radiation. Each new spectrum added to the database, helping astronomers understand the diversity of planetary atmospheres and the processes that shape them. Among the most anticipated observations were those of the TRAPPIST-1 system, 7 Earth-sized planets orbiting a small red dwarf star just 40 light-years from Earth, several of them in the habitable zone where liquid water could theoretically exist on their surfaces. Webb's observations of these planets during transits allowed measurement of their atmospheric compositions, though the first results were somewhat disappointing, suggesting that at least some of the planets might have minimal atmospheres, or atmospheres dominated by compounds other than those considered most favourable for life. The observations were difficult, requiring extreme precision to tease out the tiny signals from relatively small planets transiting a dim star, and debates continued about whether the data truly ruled out more complex atmospheres or whether the observations simply had not been sensitive enough to detect them yet. Throughout its first year of operations, Webb maintained its position at Lagrange Point 2 through small thruster firings every few weeks, tiny course corrections that kept it orbiting the L2 point rather than drifting away, a process that consumed propellant at rates that matched predictions, suggesting the telescope would be able to operate for 20 years or more before running out of fuel, far longer than the 10-year minimum mission that had been planned. The telescope's instruments performed better than specifications in most cases, with sensitivities that exceeded the requirements and stability that allowed long exposures without the drift and noise that had been feared. Problems did occur, as they inevitably do with any complex spacecraft, but most were minor, addressed by uploading new software or adjusting operating procedures, with only one significant anomaly occurring, when a micrometeoroid struck one of the primary mirror segments with enough force to create a small but detectable distortion. The micrometeoroid impact happened in May 2022, when a particle smaller than a grain of sand travelling at tens of thousands of miles per hour struck mirror segment C3, one of the segments on the outer edge of the array. The impact created a small crater in the gold coating and slightly deformed the underlying beryllium, causing that segment to reflect light slightly differently than before. Engineers analysed the damage and determined that while the impact had degraded performance slightly, it was not catastrophic, and they were able to compensate partially by adjusting the segment's actuators to minimise the effect on the overall wavefront quality. The incident served as a reminder that space is not empty, that even at Lagrange Point 2, far from the major concentrations of orbital debris around Earth, the telescope was vulnerable to impacts from natural meteoroids that could strike without warning. The question of future impacts could not be completely answered, because the flux of micrometeoroids in interplanetary space was not perfectly known, and each impact's effects depended on where it hit, how fast it was travelling, and what angle it struck from. Engineers calculated that over the telescope's lifetime, it would likely sustain dozens of significant impacts, gradually degrading the mirror's performance, though how quickly this degradation would accumulate was uncertain. Fortunately, the mirror had been designed with considerable margin, performing better than requirements even after the first impact, and estimates suggested that even with accumulated damage, the telescope would still outperform Hubble for many years to come. As observations continued and data accumulated, Webb began to reveal aspects of the universe that had been purely theoretical before becoming empirically accessible, allowing astronomers to test predictions about cosmic inflation, about the nature of dark matter and dark energy, about the processes that created the chemical elements, about the frequency of planets and the conditions that might allow life to arise. Some of these tests were direct, measuring specific phenomena that theories predicted, while others were indirect, using Webb's data to constrain parameters in cosmological models or to rule out certain classes of theories that predicted observations different from what Webb actually saw. The results were being published in scientific journals at a rate that seemed overwhelming, with dozens of papers appearing each week based on Webb data. And astronomers joked that the telescope was producing data faster than anyone could analyse it, though this was precisely what a successful mission should do. telescope's observations of the solar system, though perhaps less exotic than studies of distant galaxies, provided unique insights into the planets, moons, and smaller bodies that share Earth's neighbourhood. Webb observed Jupiter in infrared light, revealing details of the planet's atmospheric circulation and capturing unprecedented images of the auroras at its poles, phenomena powered by the interaction between Jupiter's magnetic field and charged particles from its volcanic moon Io. Observations of Saturn showed its rings in exquisite detail, with different wavelengths revealing variations in ring particle composition and size distribution, while spectroscopy of Titan's atmosphere revealed complex organic chemistry occurring in the moon's nitrogen-rich air, processes that might resemble those that occurred on early Earth before life began. Webb's study of asteroids and comets provided data on the composition of these primitive bodies, remnants from the solar system's formation that had been largely unchanged for billions of years. Spectra showed the presence of water ice, organic compounds, and minerals that offered clues about the conditions in the protoplanetary disk from which Earth and the other planets formed. Some asteroids showed evidence of having been heated and differentiated, with metallic cores and rocky mantles, while others appeared to be loosely bound piles of rubble, aggregates of smaller pieces that had gently collided and stuck together. Comets observed by Webb revealed jets of gas and dust erupting from their surfaces as solar heating vaporized ices, and the composition of this outgassing provided information about the volatile compounds that had been locked away in the outer solar system for eons. The data from Webb's first year transformed several fields of astronomy simultaneously, with impacts reverberating through cosmology, galactic evolution studies, stellar astrophysics, planetary science, and exoplanet research. The telescope had achieved what its designers had intended, providing a capability so far beyond what had existed before that it opened new areas of investigation rather than merely improving measurements of known phenomena. Young astronomers who had not yet been born when the telescope was first conceived were now building their careers on Webb data, writing PhD dissertations about discoveries made possible only by this instrument, while senior researchers who had waited decades for its launch found themselves grappling with observations that challenged ideas they had developed over entire careers, forcing them to reconsider conclusions they had thought were well established. The telescope's scientific productivity seemed likely to continue for years, limited primarily by the propellant supply that would eventually run out, though engineers had been conservative in their estimates, and the actual fuel consumption suggested the mission might last considerably longer than 20 years if the micrometeoroid environment proved benign and no major systems failed. The instruments were showing no signs of degradation beyond what had been expected, and the cryocooler that kept Miri at its operating temperature was performing flawlessly, cycling through its compression and expansion phases with mechanical precision that gave confidence it would continue functioning for the foreseeable future. Proposals for observing time on Webb continued to vastly exceed the available hours, with typical oversubscription rates of 5 to 1 or higher, meaning that for every hour of telescope time, astronomers had submitted proposals for 5 hours of worthwhile observations, and the selection committees faced the difficult task of choosing which science would be done and which would have to wait or never be attempted. Some particularly ambitious programs required hundreds of hours of observations and spanned multiple observing cycles, building up deep exposures or monitoring targets over time to detect changes and variations. These large programs were controversial because they consumed significant fractions of the available observing time, potentially crowding out smaller projects, but they also promised to produce legacy data sets that the entire astronomical community could use for years, archives of deep images and spectra that would be mined for discoveries long after the observations themselves were complete. The operation of Webb required coordination among control centers on 3 continents, with the Space Telescope Science Institute in Baltimore serving as the primary science operations center, while the Mission Operations Center at the Goddard Space Flight Center maintained continuous contact with the spacecraft. and European and Canadian teams supported their contributed instruments and coordinated their scientists' observations. This global collaboration continued seamlessly, despite time zone differences and the occasional complications of international data transfer regulations and security requirements. The data from Webb was made publicly available to all astronomers after a proprietary period that gave the teams who proposed the observations time to analyse and publish their results, ensuring that those who invested effort in developing observing programs would have first opportunity to benefit from the data, while also ensuring that the full astronomical community would eventually have access to all observations. As months passed and more data accumulated, patterns began to emerge that hinted at deeper truths about cosmic structure and evolution, patterns that required large samples to detect but which, once recognized, seemed to point toward revisions in understanding that would take years to fully develop and validate. And the James Webb Space Telescope continued its silent vigil at Lagrange Point 2, its golden mirrors collecting photons that had travelled unimaginable distances through the expanding universe, photons that carried information encoded billions of years ago in the light of dying stars and newborn galaxies, information that was only now, after journeys spanning most of cosmic time, being decoded by instruments and minds that existed because other ancient photons had warmed a planet and powered the chemistry of life.